So we saw that if we remove the weight from the piston in a piecewise manner, we could extract more work from the gas. And so we're going to take this idea and extend it to its logical conclusion by looking at the following case. So a case 3, where we're still going to deal with a gas inside or underneath a piston, where the gas is still underneath the piston. It's still at a volume of initially 0.1 meters cubed. But instead of having, a 1 kilogram block on top or 2 half-kilogram blocks on top, instead what we're going to have is a pile of sand. So this is our initial state, where we have a pile on sand on top, where each grain of sand is very small. Each grain has a mass much smaller than 1 kilogram, but the total mass is still going to be equal to 1 kilogram. So the total mass of the sand is still 1 kilogram in weight, or in mass, I mean. Okay. All right, so initially the system has a volume of 0.1 meters cubed, and what we're going to do is we're going to remove 1 grain of sand at a time. Okay? So we're going to remove 1 grain of sand from the piston. Okay? Where the gas is still underneath. And by removing 1 grain of sand, since the mass is so small, that's not really going to change the system that much. The volume is going to be a little bit bigger, but it's going to be, basically, you're not going to notice it. And it's only after we remove 1 grain of sand repeatedly, so if we gradually move, that the piston is able to rise all the way to the top, and the gas is able to reach a final volume of 1 meter cubed. Okay? All right. And so this final state, I'll call state N. But for all the steps in between, where we remove an I number of grains from the pile, we'll call that state I. Right? And so after I grains are removed, the volume of the system, VI, is going to be somewhere between V1 and Vn. Okay? And so this is the premise now. We're basically just, we basically split that block into a lot of different pieces, a lot of different grains, and we're removing those grains one at a time. And each time after we remove a grain, we wait a while. Right? Okay? And so what we want to figure out now is what is the total work required to go from state 1 to state I all the way to the final state. And then what happens if we try and go backwards? back to the initial state. Okay? And so essentially what we could do is we could apply the same analyses that we applied before, where if we estimate the pressure of the system initially of the gas, pressure of the gas, it's going to be equal to this. And if we calculate the pressure at the end, in the end state, it's going to be equal to this. But in those intermediate states, P sub I, the pressure is going to follow this relationship, where it's the total mass of the pile, MB, and then minus essentially the mass of sand, or the grain, I believe I call it M grain, the mass of each grain that you're removing. Okay? Alright, and so if we estimate, or if we calculate the total amount of work that we extract, or that the gas gives off after we remove each of those grains, it's going to follow this series-like equation, right? Where we have P of I, V of I, V of I minus 1, okay? And these Vi minus Vi minus 1, we could kind of think of this as a delta V. Okay? And so the amount of work, the total amount of work that the gas gives off is Pi delta Vi. Okay? Alright, so that's mathematically what the work would equal. But let's draw this graphically. And so, again, we have our plot. This is pressure. This is volume. We start at P1. We end at Pn. We start at volume 1. We end at volume n. Start here. Start here. And this curved line is what it would be if the pressure was following the ideal gas law. Okay? But basically, we start here, and then for each intermediate step, essentially what we're going to do is we're going to reduce the pressure and then slightly move the volume, right? So for that first, after we remove that first grain of sand, the amount of work that we extract is equal to this. And then we just repeat it over and over and over again. Until we remove that last grain of sand. And so the total work the gas exerts is going to be that area underneath the curve, right? And if we go in the reverse case, if we try to go from state n all the way back to state 1, right, it's going to look like this. Okay? And so essentially what we're seeing here is as we increase the number of, if we take that mass and only remove a little bit of it at a time, we're able to extract more work from the gas. And likewise, if we try and go the reverse way, it still requires a little bit more work to go back from state n to state 1, but it's much closer then the amount of work we were much closer. The magnitude of it is much closer to the the magnitude of the work we were able to extract from the gas. Okay, and so to write this out, okay, the gas exerts more work if we remove mass in a more piecewise fashion. And the magnitude of W backwards also decreases. Okay, so I hope the idea that if you start removing only a little bit of mass at a time, it allows you to extract more work from your system. I hope that's becoming clear. And to at least kind of tie this back to the mathematics that we were doing before, I showed that, the work in this case follows this summation-like equation where you have pressure I and then you have delta V I as well. Okay? All right? And so, in this case, if we consider the mass of each grain of sand, and we just keep reducing it so that it is basically 0 if we take the limit of it, the number of steps we need in order to go from state 1 to state n increases to infinity, right? So the smaller we make each grain of sand, it's going to take us, we're going to need many more grains of sand in order for the total mass to equal 1 kilogram. Okay? All right, so as m grain goes to 0, the number of steps n goes to infinity. At the same time, our delta V, the changes in volume between each step, that also goes to 0. And the differences in pressure between each step, if we call that a delta P I, that also goes to 0. Okay? So if we go to the next page, essentially what I'm trying to say is that if we take the limit of work, the total work, as we go from stage 1 to stage n, in the limit that n goes to infinity, what we would be taking is the limit of n goes to infinity of the summation of pi delta vi. Okay? And we'll make one small approximation. Since we're dealing with n infinity steps, I equals 2 is basically the same thing as I equals 1. So that's just a small approximation we're going to make. All right? And so we have the limit as n goes to infinity of this equation where we're dealing with a delta. But if you remember from your Calculus 1 class, the equation we have right here is the definition of an integral. Right? An integral is the limit as n goes to infinity of something times a delta variable. All right? And so what we have now is this. Okay? All right, and so basically the whole idea here, well, I'll kind of finish this off in a little bit. If we go back here, the reason, at least physically, why this makes sense is if I take a look at these delta VI and this delta PI, if we make them infinitesimally small, essentially what we're saying is the system is quasi-static. And that at each step, the pressure and volume, you aren't changing them that much, and so they're essentially going to be at equilibrium. At each step. Okay? Alright, and since they're at each step, or they're at equilibrium at each step, that allows us to then describe both the pressure and volume using what we call equations of state. Alright? And one equation of state that we could use is the ideal gas law. And so if we apply the ideal gas law to our work equation in the limit that n goes to infinity, so basically plug in the ideal gas law there and then take the integral, what we would get is nRT times the natural log of volume 2 over volume 1. Okay? And so essentially what we get is that quasi-static isothermal expansion result. So that same result that we've already seen back in MEB2 and in Chapter 3. All right, and so if the main idea here is that if you make you remove the mass in a piecewise manner, and you make your step sizes so small, you basically are able to achieve a reversible process.